Hello everyone, welcome to the video series on field theory. In the last video, we have convinced ourselves that why is it required to study fields. So now let us investigate what are fields. The dictionary meaning is that an area of land marked by the presence of particular objects or features. So similarly, what mathematically a field represents, it is a set which is marked by the presence of particular mathematical objects. It could be numbers, it could be anything else, right? So informally, we have been using field in previously also, right? In our so many subjects and everything. So field is a set on which addition, subtraction, multiplication and division are defined and behaved as the corresponding operations on rational or real numbers, as we have done in earlier classes like in arithmetic and in algebra courses in our school, right? So there are infinite number of fields that are present to us. For example, we have the field of real numbers, we have the field of complex numbers and so on. These are particularly of containing infinite elements in them, but there are certain fields which have finite number of elements also. We'll see those in the next videos. So now having defined the field, having understood what it means, let us now formally define what is a field. So field is basically a set, let us name it F for now, with two binary operations on F called the addition and the multiplication, satisfying the following field axioms. Let us see what are those. The closure under addition, that means if you take any two elements from the set F, then their addition should also be in F. And the closure under multiplication, what does it mean? It means that if you take any two elements from the set F, then their multiplication should be in the set. Basically, these two properties are intuitive because we are saying that the two operations plus and multiplication, addition and multiplication, they are the two binary operations on F. That means these come under the definition of binary operations, so we do not need to define them explicitly, but for the sake of completeness, let us write these two also, right? So now let us move on to the next properties. They are commutativity of addition. That means you take any two elements from the set F, then they two are commutative. That means if you do A plus B or you do B plus A, they are the same thing, right? As in the ordinary numbers that we have. For example, in the reals, if you add 5 plus 3, that is also equal to 8, and if you add 3 plus 5, that is also equal to 8. So this is the commutativity of addition is there in fields. Next, commutativity of multiplication. That means if you take any two elements from the set F, then the multiplication is also commutative. That means if you multiply A to B or you multiply B to A, you'll get the same results, as in 5 into 3 would be 15 and 3 into 5 would again be 15, right? Then the associativity of addition. That means if you take any three elements in F, the order does not matter. What does it mean? It means that if you add A and B first and then add C to it, or you add B plus C first and then add A to it, you'll get the same result. That is the associativity of addition, right? For example, you have three numbers 1, 2 and 3. If you add 2 and 3 3 first, then you'll get 1 plus 5 and ultimately you'll get 6. Otherwise, if you add 1 and 2 first and 3 later on, you'll get 3 plus 3, that is also equal to 6. Likewise, in multiplication, we have associativity also. If we take three elements from F, then they are associative. That means you multiply B and C first and then multiply it to A, or if you multiply A and B to then multiply it by C, they are going to give the same results, right? Next is the additive identity. What does that mean? Additive identity means there exists an element 0 in the field F such that if you add any number to 0, you'll get that same number. that is the additive identity. It means you are going to get the same number back. So it is the additive identity of the field f, right? So now let us talk about the multiplicative identity. What does it mean? That if you multiply any number by 1, you are going to get the same number. That means if you multiply a with 1, you are going to get a again, the same number. So this is the multiplicative identity of the group F. Next, let us define the additive inverses. What are those? These are that if you have any number a, these should be defined for every number inside the set F, right? So if you have some element or number a, then you must have something here so that you will get the identity of the group, additive identity of the group, right? Which is 0 in this case. So B is the inverse of A. So here in addition you clearly see if you have the number A, then your inverse would be minus of A, right? So this is the inverse. Then multiplicative inverse is what? Here basically this operation additive inverse means subtraction. That is, but we don't in terms of notation, but we don't use the word subtraction. We use the word additive inverse in place of subtraction. Likewise here in place of division we have multiplicative inverse. That means for any number a in the field f, you have another number b in the field f such that their multiplication is equal to the the multiplicative identity of the field, that is equal to 1. So here b is equal to 1 upon a, and this property is true only for non-zero numbers because the multiplicative inverse of 0 is not defined, 1 upon 0 is not defined, right? So the last property is that distributive property, which combines these two operations of addition and multiplication. What is this? It says that if we have 3 elements from the set F, then A dot B plus C would be A dot B plus B dot C, right? So together with these properties, we have the field F. So a set F with the binary operation star and dot together with these properties is called a field, right? So here one thing to note is that the additive and multiplicative identities, they are distinct. One is not equal to 0 in our case. So the smallest field that could must contain at least 2 identities, and so there is no field with 1 element, right? Moreover, while defining the field F, I have used the operations plus and multiplication, addition and multiplication. Instead of this addition and multiplication, I could have some operation, binary operation star and here star. So in that case, we are going to get different field with different kind of properties, but this is the most common field that we have with the most common operations, addition and multiplication, right? So if we have some other binary operation, in that case our identity is going to change. Instead of this additive identity, it could be something else, so that which gives A star E, I'm calling it E1 is equal to A again, and in this case it would be A star E2. I'm calling this another identity as E2 is equal to A, right? Likewise the inverses would also be changed. So the operations, this binary operations, addition and multiplication, can be replaced by any other binary operations, thus giving different fields. So now you must all be thinking that there are so many properties to be remembered. So can we have something which would be easy to remember, as if what is a field? So yes, if you are seeing this, and for those who knows what are groups and everything, so you must be seeing a pattern. if I am leaving these two properties, this one and this one, because they are intuitive because of the binary definition of binary operations. So now look at this. We have associativity of addition, we have additive identity, we have additive inverses, we have commutativity of addition. So this property with these four properties forms commutative group, right, under addition. So I'm writing this as compact definition of field. Say I have a set F and I have two binary operations. Addition and multiplication. Then the set F together with this binary operation plus is a commutative group. Moreover, if you have a look again at these properties, so this portion, commutativity for multiplication, associativity for multiplication, multiplicative identity and multiplicative inverse, they form group under multiplication, right? So I can say F together with this operation multiplication is also a commutative group defined on the non-zero elements. And in addition, we have this distributive property joining these two operations. So this is the field, right? So I think the definition for field is clear to you by now. So it's time to go for examples. For that, I'll make another video. So I'll see you in the next video. Thank you for watching.